So in this unit, we've been talking about counting, solving counting problems. And one type of counting we looked at is doing permutations, okay, where it's a way that you select and arrange. It's a way of selecting and arranging objects, and the order matters. Okay, so the object, the order, it is, just put in importance. But what if order doesn't matter? Okay, there are problems where it, like, well, it doesn't matter. So that's a different type of counting that we call a combination. So it's a number of ways to select objects or count the number of things without regard to order. And the following example can show you a different, or will show you the difference between the two. Okay? So we'll do permutation. It's a permutation problem, and if it's a combination problem. Okay? So find the number of three-letter words, arrangements, or permutations that can be made using the letters A, R, and T. Then find the number of combinations of choosing three letters from the set of letters A, R, and T. Okay? So we talked about permutations. How many three-letter words can you make? Well, you can do a list. So you can actually write out all the possible arrangements. So for A, R, and T, if I write a three-letter word beginning with A, those are the only two words I can write. If I write a three-letter word beginning with R, those are the only words I can write. And if I write a three-letter word beginning with T, those are the only words I can write. So there's 6. Okay, those are all the different words we can write. There's no other possibility. Remember, we did the fundamental counting principle to calculate. And remember the fundamental counting principle, we wrote out the positions of what we were trying to find. So in three-letter words, there's 3 positions for the letters. How many possible letters could I put here? And then I've used one up, and then one, and then multiply, and obviously we must get the same answer that we did when we listed them. Another way we talked about, and we didn't really use, this is the one we used the most, the fundamental counting principle. There's a formula. So we would write it like this. How many ways can I arrange or make 3 words from 3 letters? And then remember that formula was 3 factorial. Remember, this was n and this was r over 3 minus 1 factorial. Sorry, 3 minus 3 factorial. Three factorial is 6. 3 minus 3 is 0. I told you 0 factorial was 1. So again, we get 6. But this was the way that we did it. This is usually the best way to do it. Okay. Combinations. How many combinations are there? Well, let's start here with A, R, and T. Can you give me another three-letter word that doesn't use the letters I've already used? No, right? Order doesn't matter. If I did ATR, I've used the same three letters. Okay, the order doesn't matter. Whereas here, it matters. That's the difference between the two. So there's only one possibility. That's the main difference between a permutation and combination. In permutation, order matters. In combinations, order does not matter. Now, we can't use the fundamental counting principle for this, but we can use a formula. And what we can do to use the formula is, okay, let's pretend order matters. So if order matters, that becomes a permutation. I get 6 different ways, right? But many of those ways have repeated, haven't they? Okay, like ART is the same as TRA, is the same as RAT, is the same as TAR. So I have to divide those repetitions away, which means I have to divide by how many different ways I can arrange 3 different words. So we actually get 6 divided 6, which equals 1. And that leads to the formula to find combinations, which we will use, although you can use your calculator. And we'll talk about how you use your calculators in a second. So when we did permutations, we did NPR combinations. We're going to use NCR. And what it is, it's the permutations divided away the order. Or in other words, n factorial over n minus r factorial. That's the permutation formula. But to divide away the order, I have to multiply on the bottom or divide away r factorial. So this here gets rid of the order. Turns it from a permutation into a combination. And again, we've had restrictions on it. N has to be greater than or equal to 0, and N has to be greater than or equal to R. Because we can't obviously do negatives. And R can't be greater than N, because that doesn't make any sense. And then these are just some of the types of problems that we use combinations. Okay, so we're just going to go through several examples right now. So from a group of 5 students, 3 are chosen to work on the dance committee. How many ways can this committee be formed, or how many ways can this be done? See, this is different. A permutation question would have been, how many, from 5 students, how many ways can you arrange 3 for president, vice president, and treasurer, or something like that? The order matters. But because it doesn't matter, like maybe A, B, and C are chosen in that order, and then, or maybe C, B, and A are chosen. That's the same 3. Okay. So if we want to list the possibilities, well, let's think of all the possibilities that we can have with A. at the beginning. A is chosen first. So I could have A, B, C. I could have A, B, D. I could have A, B, E. There's no other ones that begin with A and begin with B, so there are ones that begin with A but don't have B in the middle, and that's A, C, E, and A, D, E. Or I feel like I'm missing one. A, C, D, sorry. You can just add it on the end, but I like to write it in order that I do it. So I would have done it, I should have done it like this: A, C, D, A, C, E, and A, D, E. So those are all the ones that begin with A. By trying the other ones, I've repeated. For B, I could have B, C, D. I could have B, C, E. Or I could have B, D, E. Can't use A because I've already done them up here. And then there's one possibility left without A, B, and C, and that would be C, D, E. All the other ones I've written in some different order. So that gives us 10. So if we use the formula, we should get 10. You kind of read it backwards. Like you can say it 5, choose 3, or I always say, how many ways can you choose 3 from 5? And remember, it's n factorial over n minus r factorial times r factorial. So it's going to be 5 factorial over 5 minus 3 factorial times 3 factorial, or 5 factorial over 2 factorial times 3 factorial, which works out to 5 factorial works out to 120. 2 factorial is 2, 3 factorial is 6. 120 divided 12 obviously gives us 10. Okay. Graphing calculator, if you have one. How do you do 5, choose 3? Don't worry, I'll do the other calculators as well. But quite a few of you have graphing calculators, so I'm going to start with that one. So what you do is you punch 5. Okay, now you got to find the choose function. And the choose function is in the math button. So math, and then scroll over to PRB for probability. And you should see at number 3, NCR. So choose that one. So now you've got 5 NCR, and then choose 3, or press 3 equals. And you've got 10. So that's how you do it with the graphing calculator. And usually, most times, there is some type of combination question on the provincial where you're going in the calculator section. So you do need to know how to use it on your calculator. Let me pause for a second. Yes. Continue on. So we'll do some basic combination ones. So how many ways can you choose 6 numbers from 10? So basically you're finding 10, C, 6. So you can do that on your calculator. You should get 210. How many ways can you choose 4 from 10? Because there's a reason for that. N choose R will always equal N choose N minus R. So 10 choose 6 will equal 10 choose 10 minus 6. Or 10 choose 4 will equal 10 choose 10 minus 4. Will always equal the same thing. Okay, so like, for example, if I had this, 15 choose 7, what would be an equivalent combination? 15 choose 8. Because these two just add up to this. Okay. 649, if you're not familiar with it. Okay, you choose you get 49 numbers. You choose 6 of them. Okay, and then they do a draw. If all 6 of your numbers are drawn, you win $5 million. What's the probability of winning? Well, in order to find the probability, we have to find how many possible ways are there to win. How many possible ways can we choose 6 numbers from 49? And you're going to find it's a pretty big number. 13,983,816. So the probability of winning would be 1 out of that. So that's a bit of a long shot. Okay. Now, they can get a little bit more involved. Suppose 20 students will be separated into 3 smaller groups. So we've got a group A, which consists of 5, group B, which consists of 8, and group C, which consists of 7. How many different ways can I have these 3 groups, or can this be done? So let's talk about group A first. How many students do I have right now? No. How many students do I have right now? 20. How many am I choosing for A? So 20 choose 5. That will get you the number of combinations for A. The number of combinations for B. How many? Now be careful with this one. How many students do you have to choose from now? 15. Because 5 have gone to A. And how many are we choosing for B? 8. And C, there's 7 left, right? And I'm choosing 7. Which actually, when these two are identical, the answer is always 1, because there's only 1 possible combination. So whenever you see that, you don't really need to do it on your calculator. Now, you took AP Stats with me, and probability, what would be the probability of this and this and this? And does not mean add. Multiply all of these. Or means add. So we got to find these.
Oh my God, like 997, 240.
Yeah, so this would be an example of a question on the provincial that would be in the calculator section. So 15,504 for A, 64, 35 times 1. 99,000,000. 768,240. That's a lot of ways. And then just as a note, 1 choose 1, 2 choose 2, etc. Always equals 1. Okay, so as I was saying, if two numbers are identical in this combination, it's 1. Okay. Others. How many committees of 3 girls and 5 boys can be made from a class of 15 girls and 20 boys? How do you think you'd do this?
15 choose 3.
15 choose 3 for the girls times 20 choose 5 for the boys. Yep. So that gives us 455 times 15,504, which gives us over 7 million ways. Okay. Same question, except this time, how many committees of 3 girls and 5 boys can be made if Sally, John, and Adam must be on the committee? Well, what's that? 14 choose 3, 2. Okay, so 14 choose 2. That's for the girls without Sally, because she's already on it. Girls without Sally. 18 choose 3, right? Because there's 18 boys, we can only choose 3 because John and Adam must be on the committee. So these are boys without John and Adam. Technically, you don't have to do this, but to account for the one choice where Sally, John, and Adam are on the committee, I mean, we could do this, but it's not going to affect our answer. Because there's 3 ways to choose 3 from Sally, John, and Adam. If you didn't have this, it's still right, because this works out to 1. And anything times 1 is still itself. Okay? So it's not necessary to have this. Because it's going to work out to, we got 806, no, 91 times 816 times 1, which gives us 74,256 ways. Part C. This means something different than it does in stats when we saw the phrase at least. Okay? Can't get it, you guys can't get away from that phrase. So, how many committees of 5 people can be made with at least 3 girls? Okay? Well, what are the possibilities of the number of girls on the committee if there has to be at least 3? Not 12. Like I could have a committee with 3 girls. Does that have at least 3? I could have another set of committees with 4 girls, and I could have another set of committee with 5 girls. So I've got to find 3 different things, and therefore it's one, or that one, or that one, which means add. So I have to do 3 girls. Well, for 3 girls, there's 15 girls, we're going to choose 3. Times 20 boys, we're going to choose 2. No, we're adding the categories. To find the number of combinations in the 3 girls only, we multiply. Because the committee can be made of this and this. Okay? Just follow along with me. I'll explain it at the end. 4 girls. 15 choose 4 times 20 choose 1, right? Because 4 of the committee members are now girls, which means there's only 1 male left to choose for boys. So 20 choose 1. And then for 5 girls, 15 choose 5 times 20 choose 0. There's no boys on the committee. Those are the possible scenarios. So it could be 3 girls, which I find by multiplying these 2 combinations, 4 girls by multiplying by these 2 combinations, 5 girls multiplying by those 2, and then it could be this, or this, or this, which means I add these. So I'm doing a combination of multiplying for each scenario, but then to find the total number of scenarios, I add the different scenarios. And then this is just a matter of using your calculator. So this would be 455 times 190, which equals 86,450. This would be 1365 times 20, which gives us 27,3. And this would be 3,000 times, what do you think this is? 1. There's only one way to choose no boys, and that's to have all girls. So if R is 0, the answer is always going to be 1. So we can see there's certain patterns. 3,003, and then we add these together. And we get a total of 116,753 committees. Okay. Yeah.
If you had said 20 choose 20, it would be incorrect.
Well, technically that would be a concept error because you're not understanding how to choose the boys. No, it's not there's a difference between a communication error and a concept error. Okay, a concept means you're not understanding, like even though it happens to work out to the same answer, your reasoning is incorrect. Okay, that's actually a very good question. Okay, because there is a big difference between those two. Like if you miss arrows on an asymptote, that's a communication error. That doesn't mean you don't understand what an asymptote is. You know what it is. You know where it goes. You just made a notation error. Okay. But if you put a very nicely drawn asymptote in the wrong spot, that's a concept error. You don't understand what you're not understanding what asymptote means if you don't know where to place it correctly. We are actually going to skip this page on cribbage. Okay. Because it's very similar to what we just did on the previous page. And I don't want to have to go through the whole idea of explaining how to play cribbage. Anybody know how to play cribbage? With permutations, we saw ones like this, where we had to solve, and there were certain restrictions. Okay? If you remember how we did these, we had to use the formula for these and then use algebra. So what, according to the formula, which we'll get it, is NC2, it is n factorial over n minus r factorial, and r is 2 in this case, times r factorial, which is 2. Equals 21. And now we have to use algebra to solve. Do you remember what to do first? It's very similar to what we did with the, what's that? Maybe there's something we can do else, something else we can do first. Why don't we get rid of these? Do you remember how to get rid of those? Start writing one out until it matches the one in the other, in the numerator or denominator. This is bigger than this, so start writing this as n, and then n less 1, and then n less 2. Stop there because it matches the denominator. So therefore, that allows me to get rid of the factorials. So now it just is n times n minus 1, 2 factorial is 2 equals 21. Now let's get rid of the denominator. By doing what? Times by 2. So I'm left with n times n minus 1 equals 42. No, well, 2 factorial is 2, right? 2 times 1. So I just evaluated 2 factorial. Because I don't want the factorial signs in there. This I got to multiply through. And when you do, notice you get a square. Which means you've got a quadratic equation, which the majority of the time you solve by factoring. But in order to factor, you've got to get everything by itself on one side, 0 on the other. Minus 7 plus 6, which means what are my 2 potential solutions? Are both of those good solutions? No, because remember, n and r have to be greater than 0. Or sorry, n has to be greater than 0. So that's out. Can't have a negative. And this one. Well, let's write this out using the formula. N factorial over n minus 3 factorial times 3 factorial is equal to n minus 2. Let's get rid of the factorials. So start writing the top one, start moving down by 1 until it matches the factorial in the denominator. So I have to go all the way down to n minus 3 factorial. And 3 factorial is just plain old 6. Might as well get rid of that. So those go, and I still have equal to n minus 2. If I multiply both sides by 6, I get this times this equals 6n minus 12. And then if I multiply all this through, I'd get an n cubed. We really don't know how to solve n cubed equations. Okay? Can you see something you can get rid of? Remember, whatever you, in algebra, one of the basic rules of algebra, whatever you do to one side of the equation, you do the exact same thing to the other. Can I do something to both sides of the equation to get rid of something? I can divide both sides by n minus 2. Okay? So I'm left with, here, I'll just write this, n times n minus 1 times n minus 2 divided 6 equals n minus 2. If I divide both sides by n minus 2, it will take out those. But what remains on the right here? 1, not 0. Remember, when we divide to reduce, it cancels out to 1. When we subtract to reduce, it cancels out to 0. So now I've got something very similar to the previous one. So now I can times both sides by 6. Multiply this through and I get n squared minus n equals 6. Bring the 6 over because I have to factor to solve. And I'm going to get minus 3 and plus 2, which means my potential solutions are 3 and negative 2, but it can't be negative. So only 3 is the answer. Okay. So that's combinations. And the last thing we're going to do in this unit is we can use our knowledge of combinations actually to solve algebraic problems besides this, which we'll talk about on Monday. So you should try and get as much of 9.3 done as you can.